Alright, so this is the first problem that we are looking at today. And in this case, we have been given a system and the block diagram, and then they're asking us a couple of questions about the steady state error, the system type, and yeah, and the error, we need to find that out for two kind of different inputs. So if it's a step function or if it's a ramp input. So let's start off with just condensing our block diagram a little bit. So the first step that I've already done is kind of clubbed the this feedback loop over here into a transfer function T1, and T1 would be defined by this set of expressions over here, and that's what is coming into this expression that I have, this new block diagram that I've made here. So I've condensed this T1 from this feedback loop. This transfer function is just the same as it was before. And then before that, you see that the 0.5 gain value that was there for the input as well as for the feedback loop, since they are the exact same gain values, 0.5 in both the cases, I was able to conveniently plug that in after my summing junction. So I've kind of plugged both of these values together and kind of put them after the summing junction. So this is kind of a block diagram reduction technique that I've used just to simplify our block diagram a little bit. And then after that, now I'm clubbing all of these three blocks together and calling that G. So that would be kind of bringing it in the transfer function form that we saw in our derivation for our steady state error. And as you can see, G here would turn out to be an expression like that, where I've just multiplied these three blocks together. And now if you were to write this down in the particular form that we were writing or rather using in our derivation, this can be written down as something like this, right? So we have split up the terms a little bit, or collected the terms, appropriate terms over here. So essentially we had this 1 by SG term in our standard form, and if you were comparing that with this form over here, we can see that G would be equal to 1, and this entire transfer function that's left out, this is what we are setting to G naught. And as you guys remember, in the sample that or that sample kind of derivation block diagram also had another kind of transfer function D multiplying before G, right? But since in this particular case we ended up multiplying everything together and considering that as G, we kind of simplified the process a little bit in that D turned into just 1. So this would basically tell us that D naught is also equal to 1. It would have to be. And then if we also had like another term in the denominator, which would be 1 by s raised to the power d, this would also have to be 1, and that would imply that our small d, the exponent, the power of the s term in the denominator, would have a power of 0. So we have thus set up that the value of G is 1 for this particular system, and the value of small d is set to 0. So these are our system kind of properties, and this is what is giving us our system type, right? So now we can actually go ahead and calculate the solution for part A, B, and C. So let's start off with part A. So here they are telling us that we have a step input. So as you guys know, the step input in the S domain can be written down as that, right? And if you were to compare this with our standard form of any input, you can clearly see that A is equal to 1 and L is equal to 0 in this particular case, right? And as you guys remember, for our system, we saw that D is equal to 0 and G is equal to 1. So in this particular case, d plus g is equal to 1, and that is greater than L, which is 0. And if you kind of go back and refer to that error table that we had set up, for this particular condition over here, if d plus g is greater than L, the steady state error actually turns out to be nothing but 0. So we don't even need to compute or try to do anything. If this condition satisfies, our steady state error is 0. So now let's go on to part B. They're asking us what would be the system type. So as we saw that the value of d plus g is 1, this is a type 1 system, right? There you go. And now finally in part C, we are now looking at a different input. We are looking at a ramp input, which can be written down as, in the time domain, written down as 5t. And if you were to transfer that into the Laplace domain, or the S domain, we would have 5 divided by s squared, right? So for this particular input, if you were to compare this with a standard input format, that's what we have. And A is equal to 5 in this case, and L is equal to 1. So you can see that this the value of A and L depends on our input, whereas the value of D and G kind of depends on our system. That's something that you want to kind of note and keep in mind, right? So in this particular case, we again have the value of d plus g as 1, but we are also seeing that the value of L here is also 1. So we now have one of those exception cases from our table that we had defined earlier, where the value of d plus g is equal to L and it's not equal to 0. So in that case, the error can be written down as, with this formula over here, AL factorial divided by KT G, right? And let's go ahead and kind of simplify the solution for this on our next slide. So I've written down the formula and our terms beforehand. The only thing that we need to evaluate now is this are these KD and KG terms. We know A, we also know L, right? So let's go ahead and do that. So KD would be nothing but limit s tending to 0 for d naught, and in this case, as you guys remember, d naught was nothing but 1, so this turns out to be just 1. And kg, so this here would be a little more of an expanded transfer function, so we would need to simplify this. So as you guys remember, g naught was nothing but 0.5 times k1 times s plus 3 divided by s plus 10 times s plus 10 plus k2. So we remember, or rather in the question it was given that k1 can be used as 200 and k2 can be used as 2. So we plug those in, right? And we will end up with this expression over here. And now finally, let's set our limit for s tending to 0, which would basically imply that this s here drops, this drops, this also drops. Sorry, I should have simplified this. So yeah, if when you plug in the value of k2, it would be s plus 12. And our final term here would be 0.5 times 200 times 3 times 10 times 12. Simplifying this would give us 30 by 12, which is nothing but 2.5. Plugging all of these values in our error expression here would give us, so A is set to 5, L is 1, and 1 factorial would also be 1. KD is also 1, KG is 2.5. So this gives us a final answer of a final steady state error of 2 for part C.